Hi, so in this video we are very briefly going to introduce molecular orbital theory. Okay, so you remember atomic orbitals, they can overlap and form bonds. But now in molecular orbital theory, we're going to look at how atomic orbitals in reality overlap over the whole molecule to really form wave functions that are extended over or electron waves that are extended over the entire molecule. And so these extended orbitals, these are called molecular orbitals, or we abbreviate them as MOs. So now molecular orbitals are a more complete analysis of bonds, okay, because they extend over the entire molecule. And the molecular orbitals, they include both constructive and destructive interference. I'll show you some examples. So it's a much more accurate analysis of what's going on, but it's also more complex. So I'm just going to really give you a brief preview of what's happening here. The most important rule when creating molecular orbitals, which again extend over the entire molecule from atomic orbitals, is that if you use a certain number of atomic orbitals, we'll call that number n, you will get n molecular orbitals out. So the number of molecular orbitals created from atomic orbitals must equal the number of atomic orbitals used to create those molecular orbitals. Right? Let's look at this simple example of how we create molecular orbitals. And generally what we do is we draw a so-called molecular orbital diagrams. So what we'll do here is we have an energy scale, and then so in this example we're going to look at how H2 forms, right? And so on the left we have the orbitals, on the very left we have the orbitals for a single hydrogen atom. Okay, and on the right we have orbitals for the other hydrogen atom, which gets involved, which bonds then with the left hydrogen, and then in the middle we have the orbitals for H2. So each hydrogen atom just has a 1s orbital, and then these two 1s orbitals combine to form two molecular orbitals in the case of H2. So the top orbital, the higher energy one, is anti-bonding. We'll see it has a node in the middle, and so it actually is not bonding. It breaks if you fill that orbital, it breaks the bond. But the lower energy orbital, the sigma, so-called sigma orbital, is a bonding orbital. Okay, so the anti-bonding orbital we usually denote with a star. It means it's anti-bonding, it's bad. And if you fill it up, it breaks the bonds. And the sigma is, without a star, it means it's a bonding orbital. Now we can, exactly, that's the H2 example. And you see with those gray lines, they indicate now how those two orbitals form, the two molecular orbitals form out of the two atomic orbitals. Finally, I'll show you how the orbitals look. So the bonding orbital is just a combination of atomic orbitals in with constructive interference. So you basically add up the two atomic orbitals with the same sign, and then the anti-bonding orbitals where you have different sign, so that you get a node in the middle and there's no bond. We can fill in electrons. Again, the atomic orbitals, they both have more, each hydrogen has one electron in the 1s orbital, and then when we combine it, following Hund's rule and the Pauli exclusion principle, we can fill both of these electrons now into the sigma orbital, into the bonding molecular orbital. So that gives us a stable bond because we are not filling up the anti-bonding orbital at all. Okay, and so that's why H2 is a stable molecule. If you try to do this analysis for helium-2, right, which obviously does not exist, it's not a stable molecule, the orbitals look exactly the same, but you will have, instead of filling in 2 electrons into the molecular orbital diagram, you would have to fill in 4 electrons, right, because each helium atom has 2 electrons, and then you would fill up the anti-bonding orbital, and then that breaks the molecule apart. That's why helium is not a stable thing. Okay, so now let's look at a more complex molecule. For example, bromomethane, CH3Br. if you think about this, once you see what's going on here, you will realize we're not doing molecular orbital theory all the time here, because it's really complicated. There's a lot. So how many molecular orbitals are in CH3Br? We won't even count them, but there's many. There's essentially at least as many as there are electrons in general. And there are many more than 2 MOs. It's on the order of 20 or 30. But in general, even with molecular orbital theory, it's sufficient to just look at the most important ones, the ones I draw here. And there's many areas of atomic orbital overlap. You see these 2 orbitals shown here are really delocalized over the molecule. There's lots of nodes as well, right? You can see all of the nodes. Now I'll give you some more information about these bromomethane orbitals. Again, each molecular orbital generally can hold 2 electrons, which is always the case, right? And then in the ground state, the electrons occupy the lower energy molecular orbitals, and the higher energy orbitals remain unoccupied. And so the 2 orbitals shown here are the most important ones for reactivity, whenever a reaction happens. And what is shown here is, first of all, on the left here, we have the highest occupied molecular orbital. So the orbital in the molecular orbital diagram, which has the highest energy one, which has electrons in it. So those are the most reactive electrons. Okay, now we'll see what that means a little bit later down the road in chapter 6, when we start talking about reactivity. Then if we go look at the orbital on the right, this orbital now is also important. That's the so-called lowest unoccupied molecular orbital. So we abbreviate it as LUMO. But that's the orbital which has no electrons in it. It's an empty orbital. And it's important for reactivity, but it's low in energy. Okay, the lowest unoccupied orbital. Now, you can clearly see that the orbital on the right, the LUMO, has more nodes, right? It has many more nodal planes. And so, in general, we know that orbitals with more nodes are higher in energy. So, this means that's why this orbital is unoccupied, and the other one on the left is occupied. Right? Exactly. Okay, so thank you very much for watching this video. We are gonna review some hybridization next.